very nice to be here. Yeah, today's talk is about, it has this controversial title, AI safety benchmarks do not benchmark safety. It's a bit of provocation. And I would love to hear your feedback and we can have a constructive discussion afterwards. So, let's see. Okay. So, let's talk about hammers first. So, how do you benchmark a hammer? Before we go into machine learning algorithms.
I guess you hit some nails, you see if it's working, sort of.
Okay, so how do you define if it works?
Shouldn't break.
Shouldn't break.
We should first come up with sort of several dimensions of analysis, like functionality, durability, or even sleekness.
Yeah, you want it to be durable, so you need to check the materials that the hammer is made of, and also check, as Igmar said, okay, if it, like, does it job? Does it nail the nails, and also, or does it break the wall when you hit on it? No?
Yeah. The kinds of nails or the width of the hammer.
Exactly, very good point. Like, look at the properties of the nails that the hammer interacts with to then be able to see if it works. What else do you benchmark, maybe, on the hammer?
Should give you splinters, right? Like if the wood is sort of so poorly cut and I grab it and I get splinters, that's probably not a good idea.
Yeah. So, like, you try to think about, okay, what are the potential scenarios that take place, and like make design decisions that prevent this to happen.
Probably maybe a part with safety as well, because it could be dangerous also.
So how would you then benchmark like all these things? Would you develop protocols or standards, specific experiments? All of the above, I think.
Yeah.
Yeah. Wouldn't you also like do durability tests over time, maybe, like in different walls, in different people holding it, like left-handed, right-handed individuals, etc. Okay, so it's very, actually, even for a hammer, you need to do a lot of things to have a hammer ready, and deploy it and say, okay, I can sell it and it's going to be useful to the people who use it and safe too. I will leave the hammer aside, but we will come back to it. So this is a time series from Google Trend about how often the Ngram AI benchmark is used over time. And you can see, like, after the launch of ChatGPT, or the new wave of generative AI, the use of the term has boomed. So why is the question? Like, why do AI benchmarks provide? Like, what do they bring to the community, to the engineers, etc.?
See which models performs better for a desired task.
And why do we care about it?
Because we want it to be good at doing our jobs.
Yeah, so we want to say, okay, what is developed is actually useful. Other reasons?
The investors care.
The investors care is very important, actually, because startups need to raise billions, actually, called startups. They need to raise billions in order to be able to develop the systems. Other reasons?
Maybe also about time, the timing management behind it.
In what sense, time?
The results in a specific good timing. Let's say we want to develop a project or solution in a good timing, so you use AI or maybe different models to have the results in good time.
Yeah, so they need to see, okay, what tasks does the model do actually, to see how to develop it so it can do the task efficiently. And like part of this AI benchmarking wave is like we have a lot of leaderboards for different tasks, and somebody can see, okay, how different models perform. Now, in this talk, I want to make a controversial position besides the title. Like that, when we look at benchmarks, not all benchmarks are the same. And specifically, safety benchmarking differs fundamentally from other types of benchmarking. It's not the same to say I benchmark a model on MMLU. Who doesn't know what MMLU is? Like, it's different exams in various languages, simply, and tasks, like knowledge tasks. And different to say, okay, I want to benchmark a model so that it does not generate toxic speech, for example. But in order to show that, let's start with the foundational stuff. What is a benchmark? So Moritz Hart and Benjamin Recht, they say that technically, benchmark is nothing else than just a test set. Okay? And this test set obeys the holdout principle. What is the holdout principle?
In the train test split?
Exactly. Like we should never use it to actually train the model. It should be isolated. It should be out of distribution. So then we can actually evaluate the performance of a model. Now, a benchmark has been defined also as a set of different things, which include a data set, a technical task, a metric, and an accuracy score. Okay? So, what happened? And suddenly we come to a benchmark, this definition of benchmarks from simply being a data set. Can you think of any reasons?
Well, maybe because a data set is maybe for training the model on some way, and the benchmark and the data for a benchmark is not about training of the model.
Mm-hmm. Let's say that both are out of distribution. They are test sets, so to say.
Okay.
What's the difference that suddenly we talk about a benchmark and not a data set that we evaluate our models? So it starts becoming a social process. When we talk about benchmarking, we think about as a symbol in a specific community that means something. And people act based on that. Like we will say, oh, I'm going to do research, I have to benchmark it on this task to make argument A or B. Or in order to be accepted in OIRIPS, in iClear, in ICWSM. So it's not, it transcends the technical and starts to have a different value in the scientific community. And not only that, it stops being a static artifact, but people take parts of it, they change it, they extend it, they use it in different case studies. For example, 70% of benchmark data sets in computer vision were appropriated from other data sets developed in different domains. But there is also another definition, that a benchmark is a set of things, the ones that we heard before, but also one more, a leaderboard. So now goal is not just to say, okay, we should do something in a community to showcase that our model is efficient, or it works well, or it achieves, or it performs well in a specific task, but it is a competition. We want to show that our model is the best. It achieves the state of the art in terms of performance in a specific task. This is, for example, there are challenges in Kaggle, like the Netflix prize 20 years ago, if you're familiar with it. So it's something, again, like totally different from if we think the start, that we start talking about a data set, that it's just a test set, that we hold out. Okay? Now, let's focus on AI safety benchmarks. We heard like what benchmarks in general are, and this is a definition I took from mlsafety.org. They had a competition to give prizes to people who develop efficient AI safety benchmarks. And the part of it says that, of this description here is like, there are advancements in AI, and there are opportunities, but also risks. And advanced AI could be weaponized, used in a malicious manner, cause trouble, result in harms. And we need machine learning research to find ways to reduce these hazards, and we need to measure and reduce these harms. That's a very different vocabulary than the vocabulary we described benchmarks before, isn't it? And we see that there's a clear focus on risks, on hazards and harms. These three words appear. Has anybody studied engineering here, like mechanical, electrical, whatever? Like, there are standard courses in risks that somebody takes, for example, in these disciplines about how to design the systems, how to ensure that they are safe. So these terms start to appear here too. And if we try to decompose each of these terms, risk, according to the literature, is like the likelihood and severity of harm when exposed to a hazard. So what that means, like we have a hazard, which is a danger, the potential of something being harmful, and harm is a negative outcome that we don't like. It could be anything. It could be hate speech, it could be security vulnerabilities, it could be dying from cold, it could be anything, okay? A harm. So actually the risk is the quantification of the severity of a harm together with the harm itself. Now, what does that tell us? That actually there is a qualitative difference between the rest of the benchmarks, or how benchmarks are defined in computer science, and what actually AI safety benchmarks want to achieve. We have a difference in nature. We no longer talk about capability, which is descriptive. A model can do A or B, but we are talking about damage. The model should not do A or B. So we have a clear distinction there. And then we move from technical to socio-technical, from saying we want the state of the art, the best thing in a specific metric. We want something that complies to our values that define what a harm is. And a nice example that encompasses these points together is that GPT-2 is much worse than GPT-4, but actually GPT-2 is much safer than GPT-4. GPT-4 can cause much more harm in the society. Now, we define the goals that AI safety benchmarks want to achieve ideally based on this definition. So the question is like, do they achieve them? And I'd say no. I actually claim that AI safety benchmarks do not achieve their goals. And I'm going to show it to you with some examples, 5 examples, that I show technical, epistemological, and socio-technical concerns. Okay, the reason number 1 why AI safety benchmarks failed benchmark safety is that AI safety benchmarks do not follow principles of risk management. We saw that we adopt a risk vocabulary, but the processes that we are using come from pure computer science. Okay? We have a task, we have a data set, we have a metric, we evaluate accuracy. And a nice way to see that is like using the Rumsfeld matrix. He was a politician 20-something years ago who in a speech he made in an interview defined this matrix of known unknowns, known knowns, unknown unknowns, and unknown knowns. And we have 2 dimensions here: the level of understanding we have about the situation and the level of awareness we have about the situation. So known knowns are things we are aware of and we can understand. And if we do risk management, then this is the most easy thing to deal with. No? We know a situation, we know it exists, we understand it, we can deal with it. But there are other cases too. There are known unknowns. There are things we know, we are aware, but we don't understand them. Can you give an example? It could be anything. the human brain, okay? We know that we think, we don't know how we think, okay? An example. But we also have unknown knowns, things we aren't aware of but we understand, okay? So for example, when we design a building, we know that an earthquake can come, but we aren't aware how, when, etc. So we have to design for it. Like, we understand how earthquakes happen, but we don't know the mechanisms that they will appear in a specific instance, nor in time, nor in space. And we have unknown unknowns that we generally don't know at all anything about them. So if we put machine learning benchmarks here, let's say we want a machine learning benchmark to deal with known things in terms of AI safety and unknown things in terms of AI safety. Actually, machine learning benchmarks only cover two things. Known knowns, like, for example, the jailbreak bench. We know that specific prompts result to the jailbreak of LLMs. So we are going to use them to see if other LLMs will result in jailbreaking too. And also in unknown knowns. We know that LLMs suffer from bias, but we don't know specifically in which situations and how. So we can try with specific scenarios to find these biases. But then we don't know how to deal with unknowns at all. We cannot benchmark something that we don't know, even its existence. We cannot design something against it in terms of computer science benchmarks. But also in these two cases that theoretically we have the knowledge, the benchmarks we built are limited context of application. Like if you go to BBQ, that it is a bias benchmark, it has some generic prompts in English and tests stereotypes. But it's totally different testing a model in that case, and totally different, for example, having the model deployed in an insurance at the back end of a decision-making system. Reason number 2, AI safety is not probabilistically quantified. This is the term that I said before. This is how risk is defined in risk science. It is the probability multiplied by the severity. If I have a breach and I want to see the risk that the breach entails at a specific moment in time, I measure, okay, what can happen to the breach, like collapse fully, or like the lights go off, or whatever. So I calculate the magnitude of the harm together with the probability of that happening. So then I can say, okay, this bridge is risky. Let's block it, not let people go through. And similarly, there is like in the operationalization of this process, like different than, let's say, models or frameworks to decide how to act based on probability and severity of incidents. But the traditional benchmarks don't do that at all. The only thing they measure is success rate. Like, we have some examples, we feed them, we measure, okay, in 70 out of 800 cases, this is what happened. And actually, to show that to you, we evaluated 20 AI safety benchmarks, and this is what category they use to quantify their risk. And most of them are empirical. So percentage rates of failure, given the data provided in the benchmark. There is one case, the AI Illuminate from ML Commons that was recently released, that they use grading scales like the previous one, but what they do is like they compare as baseline safety the performance of GPT-4, which it's very, again, that comparing it to a state-of-the-art model does not mean that that model is safe. So you don't actually quantify a probability about how safe your system is not if we put it in the real world. And then again, like we have attack success rate, and we have also, for example, in truthfulness, how many times a statement has been truthful or not, but in that case, truthfulness is not even like binary or ground truth itself. It's qualitatively described. For example, mostly truthful statement, less truthful statement, etc. So we see that we lack this quantification and this rigor to pass from measuring something to quantifying the probability that something risky might happen. Now, reason number 3 why AI safety benchmarks don't measure safety. AI safety in itself violates measurement theory. What is measurement theory? This is an abstract from an old medical paper. It's practically the thought process and the rules we deploy to assign numbers to a specific social phenomenon. And why do we need it? We need it so we can understand the usefulness and truthfulness of a specific scientific theory or a mathematical model. Now, why does AI safety violate measurement theory? First of all, we have the construct validity issue that most benchmarks suffer with. What is construct validity? We measure something which we assume it's a proxy of a real-world phenomenon. If we measure jailbreaks with a benchmark, we assume that actually hackers are going to use other jailbreak prompts with the same frequency and have the same qualitative characteristics as the one we are using. Okay? But that does not hold if we say, okay, in the real world. So furthermore, there is a lack of measurement standard. Okay? What does it mean that I make a less or more biased model in a specific case study? Because it changes when we change the social environment, how or more or less biased the model is, for example, and how big or small is the impact to the individual. So a specific bias might have a much higher impact in a specific scenario over another. Then safety is as an absolute concept doesn't mean it's not real. What does safety mean? We can ensure that the risk is eliminated 100%. We assume like a sandbox environment, which does not happen in real world. And third, safety is not only about passing specific tests we have defined, it's also about handling this uncertainty. I feel safe with my partner because I know they will take care of me. So they are doing something. So safety in itself is not described 100% by a machine learning benchmark. Reason number 4, AI safety is an emergent system property. What does it mean? Safety arises when system components operate together. An example of that is AI in hiring. Let's say we have a model that assigns sentiment score to the voice of an individual. And there are these companies that they say, okay, send a video of the candidate and we will tell you if it's a good job candidate or not. And they might take into consideration the individual's voice, speech, etc. So somebody's voice is unrelated to safety, actually, if we think about it generally. But in this specific scenario, if the model is biased based on the voice of individuals, it will result somebody to not take a job or lose an interview. So they will be subjected to harm only when the model is deployed in this specific structure, in this specific social context. And as Narayanan and Kapoor say, safety is not a model property. Imagine like an email, a phishing spam email. What is a phishing spam email? A normal email. It's no different than a normal email. What is harmful in it is the link or the website it will redirect you to, where you are going to click and give your information there. Or there is this big debate about true and fake news and their dispersion in social media. But for example, studies show that truthful information that it is used in a misleading way can result to much more manipulation than false information. So the quality itself of something, isolated from its environment, does not necessarily can tell you 100% about whether it's going to be safe or not when it's deployed in that environment. And reason number 5 is that AI safety is socially negotiated, or it should be socially negotiated. So Ulrich Beck, a German philosopher who used to be very famous, I hope he will stay famous, he studied a lot nuclear energy and risk, and he said that an acceptable level of risk should involve societal definitions, because it is important for the society, and not technical measurements. How machine learning benchmarks are built now is like there are 3 PhDs in a lab, they take some data they find online, they sit and label them with an LLM, they go through some examples, they publish it, and then thousands of machine learning researchers use these benchmarks in order to say, okay, my model is safe or my model is unsafe. Furthermore, what is acceptable should be defined again by the society. Let me give you an example. So, a company might say, my AI agent is safe because I tested it, and when you use it in the workplace, it does not leak information, or it does not make mistakes and does wrong financial transactions. But maybe the harm would be itself the existence of the AI agents that takes the job from another person for the society. Benchmarks thus are not developed by and for communities, and this, using technical terms to assign meaning to risk, leads to a legitimization of the risks themselves without taking into consideration the society. For example, using as baseline the safety of GPT-4, it means that we assume that GPT-4's behavior is acceptable, but we haven't asked the people or the communities if they accept that, and in which cases. So, as a conclusion, AI safety benchmarks, despite their popularity and importance, do not fully achieve their stated safety objectives. There are significant gaps in terms of rigor, engineering design principles, and socio-technical considerations. And we need to think about new ways, new methods, new definitions in order to operationalize safety in a way that conforms to the actual social needs. And going back here is like to the hammer, is like we need to treat models as we treated the hammer. Deployed in different scenarios, see how it works over time by different people, see how it interacts with individuals, see what element it possesses and which it should not possess. Thank you very, very much.